Hello, this is Concrete Path. Here we have compaction of soils. And one of the factors that was affecting the compaction of soils is that compactive effort. It is the compaction energy, actually. We can say this is the compaction energy. How much compaction energy you are applying on that soil. Energy per unit volume. So if I have that particular gamma dry versus water content, let's say that your compaction energy was initially CE1, and corresponding to that you got the curve in this way. This is your curve corresponding to compaction energy CE1. There was some value of optimum moisture content. Let's say that this is your optimum moisture content OMC1. At that time you got gamma dry max 1. So this is the data we got. Let's say that there's one more compaction energy such that your compaction energy is more. Let's this we can think it this one. Let's say that CE2 is greater than CE1, similar to that of that modified compaction Proctor test, and first one is your standard Proctor test. Similarly, it is heavy Indian standard compaction test, and this one is your light compaction test. So we can think of that way. So for the compaction energy CE2 greater than CE1, so for that your gamma dry goes increasing. Gamma dry is going to increase. Your gamma dry is going to increase such that the final curve developed is in this way. So here we would say your gamma dry has been increased. So your gamma dry max, we can write gamma dry max 2 has been achieved. And at that same time we are having some optimum moisture content. We can call that as OMC2. Okay. So we can conclude that on increasing compactive effort, gamma dry of the soil increases. Gamma dry of the soil increases, but optimum moisture content decreases. That means water content decreases. For achieving that gamma dry max, your water content decreases with respect to the initial condition. So that is the final conclusion that we can have. So if we talk about that different kinds of soils, let's take the same graph, same plot for different kinds of soils. For different kinds of soils. For different kinds of soils. So let's say that we have well-graded gravel. Let's say this is the graph for well-graded gravel. And similarly we have a few more graphs. 1, 2, 3, 4, 5. Let's make it in a better way. Let's make that in a better way. We say that first one is your well-graded gravel. After that we can have well-graded sand. We can have silty, low compressible silt. After that we can take Cl and Ch. Okay. Now we can have few conclusions from this curve. I would say that gamma is going to increase. Gamma dry is going to increase more and more if your soil is well-graded soil. Well-graded. If your soil is well-graded, your gamma dry is going to get increased. So that means we are having well-graded sand means well-graded soil means we are having that curve, we know, particle size distribution curve. So we are having all range of particles are in the soil. All range of particles are in the soil. So that means if there is a soil mass, we're having bigger particles. Okay, we're having bigger particles, and in between the bigger particles, we are having few voids. We're having few voids. Let's say that the voids are filled by now other particles of size less than that. And I would say that once those voids are filled, now we are having the voids between those small particles. Let's say that those voids are filled with now other kinds of particles. And for those also we would say we are having little bit of voids. They are also filled by particles lesser than that. So there is more and more packing. More packing is there. More amount of solids can be packed. More amount of solids can be packed. That's why gamma D increases. So for your well graded gravel, so that is your gamma dry increases. So for, I would say for your, if I want gamma dry to be increasing for your gravel, so I would say your gravel should be well graded. By that I would say, I would mean that fineness should be, number of fineness should be more. Number of fineness should be more. So percentage fineness should be more, such that the soil becomes uniform, such that the soil has become uniform, because the fines are going to fill the voids. You can see that if you have those fines, and fines are also having those range of particles, that means one of the they can fill one of the size will fill another particular void, and the void of that particular size will be filled by one more particle which is having size lesser than that, so on and so on. Okay, so that's why we can get the gamma dry to be maximum. So for the well graded gravel, your gamma dry is going to increase if you have that percentage fine is more. And similarly we can say for the sand, after that we can see, from that, if your clay is there, for the clay, as the plasticity increases, your gamma dry goes to decrease. Gamma dry decreases as the plasticity of that soil increases. Not we don't have to write plasticity. I would write compressibility. We can write compressibility. I would prefer compressibility. That's ml. Low compressibility, high compressibility. So compressibility, we can write compressibility. If the compressibility increases, gamma dry decreases for that soil. Gamma dry decreases for that soil. Also, we can say that that's plasticity. That's plasticity. Yeah, compressibility, we can also relate it with plasticity. Let's say this is plasticity. So this is all about that different kinds of soils having different those curves for your gamma dry versus optimum moisture content. Okay, let's take a problem that simple problem we can have. That 1 mark problem. Get the gamma dry max for the theoretical condition. If your G is 2.7, OMC is 16%. So I would say your gamma D max theoretical is actually at degree of saturation equals to 1. That equals to G gamma low by 1 plus WG divided by S. S is equals to 1, so we can substitute. That is your solution. Now, one statement we can write that your optimum moisture content for clay soils or fine grained soils, we can say that these are your clay soils, is actually more than optimum moisture content for sands. For granular soils, we can write granular soils. Okay. Let's talk about the compaction of sand. So our all that stuff was saying that this is the curve. This is the curve that we get for the soils, and we were saying this one for fine grained soils. If I particularly now talk about that compaction of sands, if I talk about the compaction of sands. So here the diagram is not same as that of the V, inverted V. Here we get a little bit different. Let's say this is your water content, and there we have gamma dry. So our diagram, our plot, our curve becomes that we have particular value of gamma, and this goes to decrease, and finally this is increasing again and attaining some value. So then after that again goes to decrease. So this is the value of, this is the curve for your sands, gamma dry. Let's say we got one of the value here, gamma dry 1. This is corresponding to, if the water content initially was 0, at that time we would say this is air dry condition, and at this condition we can say this is saturated condition, fully saturated condition, where your peak is observed, peak fully saturated. We can have two different values. Maximum value, we can see that one of the maximum value of density is at when water content is 0, and one of the value when water content is such that your degree of saturation is 1. Your degree of saturation here is 1. After that, when the degree of saturation is 1, and but we are increasing the water again and again, then we have again that gamma dry goes to decrease. And from this curve we can also see that we are getting some minimum value of gamma dry. Gamma dry equals to minimum. So add some value, add some water content somewhere here. So here the water content is actually 4 to 5%. Water content here is 4 to 5%. Let's talk about that. Let's talk about that curve. Let's talk about that curve. Let's talk about that curve. I would say as water content is less, as water content is less, at that time what's happening? At that time what's happening? So let's say that water content is less, and by meaning of that less, I would say that I would say that 0 to 5%. Let's say that greater than that water content is in the range. Water content is in the range 0 to 5%. Okay. Let's say that as the water content is less, that is in the range 0 to 5%. 0 to 5%. At that time, what's happening actually? If there is sand, I would say if the sand is fine, if the sand is fine, we have the concept of capillary action. We have the concept of capillary action in the sand, capillary action in the fine sand. So we have these sand particles, and because there is capillary action, there is rise of water. Capillary action saying that we have rise of water, rise of water, rise of water because of capillary action. We are going to talk about that also. And I would say at that time, if there was a little bit of water, this water develops pore water pressure. This water develops pore water pressure, and it's not allowing. If there's this pore water pressure, this creates that menisci. We can write a menisci of water gets developed. Menisci gets developed, and if you try to if I want close packing of those sand particles, if I want close packing of those sand particles, it's not allowing actually this water layer that's called as menisci. Let's say this is layer of water. It's not allowing that particles to come closer. So we can write that as water content is in this range, those menisci, that is actually that layer of water developed. It's not allowing. It does not allow close packing of water. Does not allow close packing of particles. Does not allow close close packing of soil particles. Okay. Okay. As water content is in this range, those the pore water pressure because of the capillary action. So we can write this is actually because of pore water pressure and because of capillary action. That pore water pressure is not allowing us to allowing that those particles to come closer. That's why gamma dry is lesser. So that's why gamma dry is going to decrease, and this effect is maximum. This effect is maximum at water content in the range, and gamma this effect is maximum. We can say this effect is maximum at water content is at a water content of 4 to 5%. So this effect is maximum at a water content in the range 4 to 5%, somewhere here. So here somewhere here we're getting this effect as maximum. That means here the density we are getting less. We are getting the less density. We are getting less density. So finally we can write water content was less. Uh, so because of that, your what you call as pore water pressure got developed because of capillary action, and that's not allowing that close packing. Close packing is not there. Close packing is not there. So finally, your gamma is going to decrease and decrease and decrease, and this effect is predominant at a water content of 4 to 5%. And this effect we can call it as bulking of sand. This is we call it as bulking of sand. Okay. Because of this bulking of sand, that means a little bit of water we added. Because of that, your density is going to decrease in the sand. The density of the sand is going to decrease. But that means your volume of the sand is going to increase. By bulking, we can say your volume of the sand is actually increasing. Okay, so that's your bulking of sand. Now if we now increase, now if I try to increase the water content from 5% to such that degree of saturation becomes 1. Let's talk about the part that's this part of the curve. This part of the curve. That means Now if the water content is greater than 5%, so now I increase the water content, okay, up to degree of saturation equals to 1. I want to talk about that. So I would say that those menisci which were formed initially because of that pore water pressure, uh, menisci formed because of capillary action are now broken now, are broken now. So one is that layer of that water, this is actually the layer of water. This is that water layer of water. So this layer is actually what is that? That is broken now. And now we can say the particles can now soil particles can be now easily packed. Soil particles can be easily packed now. Can be packed more efficiently now. Packed uh, in a better way. In a better way. So that means they are now coming closer and closer and closer because water is now increased such that menisci are broken. So that fluid, that thin film of that water is now broken such that you are only left with those soil particles, and there is free water. And free water can easily move. That can easily move. So finally, you are getting more dense soil, more dense sand. So such that your gamma dry is going to increase up to this limit. Then when degree of saturation was maximum, degree of saturation was 1. After that, there is again that we the same effect which was given by Lime's explanation, for fine grained soils. That is the if I now increase the water content greater than such that degree of saturation is equals to 1. After that, if I try to increase the water content now in this range, so in that range, your water replaces sand. Water replaces sand now. So because of that, your gamma again decreases. Okay, your gamma again decreases. So this is the all stuff related to the sand. We say that this mechanism is given by Lame's double layer theory. This is Lame's double layer theory. Yeah, this is given by Lame's double layer theory. So this all stuff we write it as this is double layer theory given by Lame's. So we can write Lame's double layer theory for sand. This theory is not applicable for gravel. I would say this is not applicable for gravels. This is not applicable for gravels because that gravels don't have the same procedure, same mechanism as that of a sands. The way sands absorb the water and show that mechanism, this way we don't have for the sand, for the gravel. So this is the double layer theory that's applicable for sands and not for gravels. So that's your compaction of sands, and the concept because of that concept given by Lamb is okay. Now we can observe, now we have two different values of gamma dry that are maximum somewhat. Let's say that we got here some value of gamma dry 0, and we have this one gamma dry s, and they are almost the same. Let's say they are almost the same. So if I try to have that difference of the two, we can write that your gamma dry saturation minus gamma dry at 0. Let's take the mod. That's very negligible value. This is negligible value. What this means is actually that either we can compact the soil. We can either compact the soil if the soil is in dry condition, or we can compact the soil such that it's completely saturated, fully saturated. So we can write the statement that for the sand, we are going to vibrate the sand. So for the sands, we compacted the soils by vibration. So for the sands, so sand is compacted either on dry side, compacted on dry, either in dry state or in fully saturated state, fully saturated state, fully saturated state. So this is the statement we get, that sands are either compacted on dry state or in the fully saturated state. But what about the clays? Clays are what you call as compacted such that we are getting gamma dry maximum, and that is at a particular value of water content equals to optimum moisture content. So I would say your clays are a function of water content. But your sands do not define sands compaction or not. Sands compaction is not defined by water content. So we can have the final statement: sand is compaction. Uh, is not defined by water content. Is not defined by water content. So there is no effect of water content we can have for the compaction of sands, because we now got that statement directly. We directly got that statement now that compaction of the sands would be either in the dry state or in the completely saturated state. We won't be taking a value of water content where there is some value of water. We won't take some any value anywhere. We would go either at a dry state or in a fully saturated state. Okay. Let's try that what you call as effect of compaction on properties of soil. Effect of compaction on properties of soil. Effect of compaction on the properties of soil. Okay. Let's say that what about the structure? Let's take the first one, that what about the structure we have? What about the structure? Let's make a general diagram that this was your dry side of optimum. Dry side of optimum, this is your wet side of optimum. And I would say your structure was becoming flocculated in dry side, flocculated in dry side, and dispersed in wet side, dispersed in wet side of that optimum moisture content. So that's your structure. Okay. Let's talk about that. Let's talk about that what you call as permeability. So here in the flocculated we have net attractive forces, and in this case we have net repulsive forces. Net repulsive forces. Let's go for the second one. That's permeability. That is the flow of water in the soil. Permeability. K. So permeability, I would say, because we have flocculated structure, we have more permeability. We have more permeability. K more in the wet side. Let's say that this is wet side. Let's say that this from this side we are going to talk about dry side, and this is from the wet side. A general perspective we are going to take. So permeability would be more, but we would say that permeability is isotropic. That means we would get almost the same value of permeability in all directions. Permeability would be same in all directions. But if I talk about that, what you call as dispersive structure, that's on the wet side. Here we can say permeability is more. Permeability is more in the horizontal direction, but your permeability in vertical direction is less. Permeability in vertical direction is less. So that is anisotropic permeability in this case. But overall value we can say less as compared to the dry side of optimum. We can say in the wet side of optimum we're having what you call as we're having less permeability as compared to the dry side of optimum. Let's say that this is the dry side of optimum and this is your wet side of optimum. Let's go for the third one. That's what you can call as swelling of that soil. Swelling of the soil means increase of volume on addition of water. Increase of volume on addition of water. So here we can say that soil is deficient, water deficient. On dry side, soil is water deficient. So once I increase the water, if I increase the water, what's going to happen? So volume might increase. So volume would increase. So volume increases in the say. So that means swelling is more. Swelling is more in this side, but swelling is less in this side, because it is already occupied by water. So swelling is less in this side, wet side of optimum. If your soil is compacted on dry side of optimum, your swelling for the soil would be more. Your swelling for the soil is more. Swelling is more. Let's talk about that what you call as shrinkage. We can have one more, that is shrinkage. Shrinkage. Shrinkage says that decrease of volume. This is the increase of volume on addition of water. This is the decrease of volume on reduction of water. Decrease of volume on reduction of water. I would say here we have less water, so there would be less shrinkage. Less shrinkage because we don't have water. We don't have less. We would be having less shrinkage. If our water was there. If the water is lost, that means shrinkage is more. So shrinkage is more in this case on the wet side. If your soil is compacted on wet side of optimum, you would be having more shrinkage as compared to if the soil was compacted on dry side of optimum. Let's go for one more property, that's compressibility. compressibility, compressibility. So we see that your structure in the flocculated side, on the dry side, we have flocculated structure, and it offers more resistance to compaction. Your flocculated structure offers more resistance to compaction. That dry side offers more resistance to compaction. Resistance to compaction. So compressibility here would be less. So compressibility, I can say compressibility would be less from this side, but your compressibility would be more for the other side, but more. So I can write settlements are more. Settlements are more. I can have compressibility is more. So here we also write that this is for the initial case. That this is for the initial case. This is for the initial case. When the stresses were less at low stress, at low stress. Now if the stress is more, if the stress is more, that means if the static pressure applied, if the pressure applied on the soil, if the pressure applied on the soil mass is heavy, if the pressure is more, if the pressure applied because of compact effort, static pressure we can say, if the pressure is more, it's now going to break the bonds. So once the bonds are bonds are broken, the volume is going to change tremendously. So volume increases, volume is going to decrease, change in volume would be more. Change in volume would be more. Because the structure we can say it was not in a proper way, but the bond was making them stable. Bond was making them stable because of electrostatic forces of attraction. Once the bonds are broken, we can have that more number of voids are initially more. So that means your volume now is going to decrease very much. Volume decreases very much. So finally, that means compressibility would be more at that time. So compressibility would be more. So delta is more at that time. But in this case, at that time, if you compare with respect to dry side, delta at that time would be more. But in the case, if the stresses were low, that means bonds are not broken. In the initial case, bond is not broken. Bond is not broken. At that time, your compressibility in the dry side is less, but on the wet side, we are having more compressibility in the initial case. But if the stresses are more, your compressibility is more in the dry side because bonds are broken, so your decrease of that volume is more, your decrease of that volume is more. That's the compressibility. Let's talk about the what a property that is stress strain relationship. Stress strain relationship. So we have that graph stress strain. Now in the dry side of optimum we have sharp peak. That's you can say we can have this much amount of that this kind of curve developed. That means we are having that modulus of elasticity E value. That's E for the soil is actually more in this case. Slope is more. E of the soil is more because slope is more. And the failure we can say failure is brittle. There is brittle failure of that soil on the dry side because the soil is stiff. Brittle failure is there. If we talk about that wet side of optimum, we can have a curve. We have a flatter slope. I would say flatter curve is there. Because of that, your value of E is also less. Your modulus of elasticity is less, but your failure is ductile. So we can have a general perspective that ductile failure is there on wet side of optimum. That failure is ductile. And we write that if the bonds are broken, that means at higher stresses, at higher stresses, bonds are broken. Because bonds are broken, so it doesn't matter now. So bonds are broken, so we would say that strength in both sides are same. Strength for both sides are same. So this is your general idea about the properties of that, what you call as property of soils, because that how they are affected by the compaction, how they are affected by the compaction. Okay. And now, if I have one more thing, that's pore water pressure. One more property there, that's pore water pressure. Pore water pressure. I would say in the dry side we are having less amount of water, so less pore water pressure develops. And in this side we would say your pore water pressure develops more. Pore water pressure, that's what you can say high on the wet side of optimum. Pore water pressure. That's all about the properties versus that compaction. Properties versus compaction. Let's go for the little bit of one more thing, that's if you try to compact the soil in the field, so till now we were saying that we are compacting the soil in the laboratory. Let's say that compaction in the field. Compaction in the field. So we would say in the lab we were taking that we had to achieve that gamma D max at optimum moisture content. This was the goal, to achieve a particular value of gamma D max at a particular value of optimum moisture content. Now I would say your field conditions are not strict. We don't have the field strict conditions. We don't have the strict conditions in the field. That means we can have little bit of leniency. So specification says that in the field, if you try to perform the tests, you can target for 90 to 95% of gamma dry as that of a lab. Okay, this much amount of is achievable in the field uh, with respect to the lab condition. Now we say that which of the method we should apply for a specific soil. So that is actually a function of soil. Which kind of method of compaction we have to apply? So we have different n number of methods for your compaction, and we have few soils also, few types of soils also. So we need to say which method is suitable for particular soil and particular project. For that, let's go for a little bit of uh, discussion. Let's go for that. Let's say that we are having a particular rule of that. We can say that's rammer, or we can say that's tamper. This is a tool for compaction. Compaction tool we can write. Let's say that this is compaction tool. Compaction method. We can write compaction method. So by the action of rammer or tamper, this is suitable for all soils. For all soils we can have. For all soils, and this is used in the projects. If the nature of project is that if the site is narrow, narrow site, we can write what we can write confined areas. Confined areas. If the area is confined, similar to that of basements, if there is little bit of that fill near the basements, be, behind the retaining walls, so we can have those confined areas. So at those projects we can have that use of rammer and tamper for all kinds of soils. If I take that one more kind of compaction method, let's say that smooth wheeled roller, smooth wheeled roller. So this is suitable for gravels. This is suitable for gravels, gravelly soils, crushed rocks, sands, crushed rocks for sands. So this is used somewhere. We have seen this one somewhere. Somewhere we have seen this one. So that's your road construction. So let's talk about that. Your roller is that what you call it pneumatic tire roller. Pneumatic tire roller. So this is used for your what you can say sands, gravelly, siltous, clay soils. Clay soils, crushed what you can say gravelly silts. And this is used for most of the constructions, most of the construction projects, most of the projects we can write. In general use, we can have this pneumatic tire rollers. You can see that this is used in most of the projects like that of embankments, dams, etc., etc. So that's your pneumatic tire rollers. Let's talk about that. What you can say, sheep's foot roller, sheep's foot roller. So we are having some sort of foot kind of those tires. So that impact needing type and impact type needing and impact action, because this is used for clay soil, for the clay soil. Let's say that we are designing we are having the construction of dam or earthen dam. Earthen dam is there. Okay, core of the earthen dam. At that time we can use sheep's foot roller for the compaction of that clay soil. Let's have the final one that we can say vibration. vibratory rollers. So that would be for the sands. Let's say that we are going for the oil tanks, storage, oil storage tanks, oil storage tanks. For for the embankment of those, this is actually oil storage tank is not of the sand. For I had to make an embankment for this storage tank, embankment for that oil storage tank, embankment for soil oil storage tank. For that, I have to use that vibratory rollers. So that's your compaction in the field. Let's say that we have a project, and I want to tell me, you want to tell me, you should tell me which side of optimum you should prefer that particular. You should compact the soil. Let's say that I have a project of core of the earthen dam. I had that compact core of earthen dam, core of the earthen dam. So actually, if there is a dam, let's say this is your dam, and but the system is that we have two kinds of that we can call it as embankment or dam. The core of that it should be compacted. It should be compacted by some method. It should be compacted by some method size that because this is earthen dam, so I had to ensure that there is a flow of water through this one. There is no seepage of water. There should be no seepage of water through the what you call as through the what you call as through the earthen dam. That means there should be no water allowing no water should be allowed to pass through this core. No water should be allowed to pass through this core. So that means permeability should also be less. Permeability should be less. Seepage should be less, and we can say cracking should not be there. Cracking should also be less. So if I have that property that permeability is less in what side of optimum? If I talk about that permeability, we have that flocculated structure and we have that dispersal structure. In what side we have permeability more? I would say in the dry side permeability was more. Permeability was more, but in the wet side permeability is less as compared to the permeability is less as compared to the wet side, as compared to the dry side. So your permeability in the vertical direction is less than permeability in the horizontal. So we can prefer that your soil should be compacted on the soil user for earthen dam core that should be compacted on wet side of optimum. I can have that. So I can write here that soil compacted on. We can have the answer that wet side of optimum, on wet side of optimum. And reason we can write reason. What is the reason for that? Reason is that our permeability should be less, cracking should be less, cracking in the core should be less, permeability seepage should be less. Okay. Now let's say that our project is that I want a homogeneous embankment. Homogeneous embankment. For that, we should have a strong that embankment means that it should retain something. Embankment means it should retain something. Let's say that. So here we can say your pore water pressure should not be developing. Pore water pressure should not develop much. So we should prevent pore water pressure. So pore water pressure should be prevented. Pore water we have to prevent. And this one, because this is the embankment, it should retain that particular something. There should be something to retain from this embankment. So I would say that material should be strong. So this structure should be strong. Structure should be strong. So that means strength and pore water pressure should be less. Strength and pore water should be less. Pore water pressure should be less. Strength should be more. Strength should be more. Pore water pressure should be what you call as pore water pressure is less. But if I compare that initially with what we studied, we saw that your pore water pressure was less on dry side of optimum, and your structure, because of the interlocking, your strength was more in the dry side of optimum at lower stresses. Your strength was more. So we would say your for the homogeneous embankment, I would prefer dry side of optimum. Dry side of optimum, because your pore water pressure is less in the dry side and your strength is more in the dry side. Let's go for the third one. That is, we call it as subgrade for your pavement. Subgrade for pavement. That's actually for the road. We're having that one, three, four different layers of that. What you can call it as, this is your road. cross section, and this we call it as pavement. Let's say that subgrade is there. Let's say that this is your subgrade bottom layers. Let's say that subgrade is there. Subgrade. For that, what is the thing we need to prevent? Let's say that this is a road. This is your road, and that it's having unevenness. This is unevenness. That is because of if there is little bit of volume change in the soil. If there is volume change somewhere, let's say that here volume has increased, volume has decreased here, shrinkage, swelling, such that uh, your car is there, and you are there, you are getting up and down, up and down. Okay, so that means swelling and shrinkage should be less. So swelling and shrinkage should be less. So I would write, I would say, I should prefer, I should prevent swelling. I should have swelling that is less. That is volume change should be less. Volume change is less. Volume change is less. We should not we should not talk about the shrinkage. We should not talk about the shrinkage. That means we are having some water in the soil, then after that we want to shrink it. No, we are not talking about that, because road is already constructed that above the water level. This is always constructed at some high level with respect to the original level of the that field. Let's say that this is your field, but your road is constructed above that because of that raising of that embankment we have seen. This is your actual ground level, but your road is actually above that by some 1 2 meters. Let's say that this is 1 meter, so there is no problem of water entering into that road, no problem of water. That means no shrinkage. But if there is swelling somehow, if there is swelling somehow, so I should prevent that. So swelling, I want to limit the volume changes. To limit the volume changes, I should limit the swelling. To limit the volume changes, swelling should be less. Swelling should be less. So for that, I have to say, I would prefer dry side. Should I prefer dry side, or should I prefer wet side? I would prefer wet side. On wet side, we don't have more swelling. I would say swelling is less on wet side, so I would prefer wet side of optimum. Your soil should be compacted on wet side of optimum. Okay. Okay. Let's take few problems. One, two, three, 4. Let's try to get few problems here. Let's take one of the problem. We have Proctor compaction test. Proctor compaction test is there. Soil is having that soil. We achieved that soil gamma bulk equals to 19 at moisture content of 15%, and we need to get degree of saturation. If the soil solids are having specific gravity 2.7. Can you get the answer? So I can write that gamma bulk is actually 19 divided by 1 plus, yeah, let's try to write the equation. We have the equation for gamma bulk equals to 19, and that is actually equals to G plus SE divided by 1 plus E times gamma W, and that's actually G 1 plus W. In this way we can write. Can you get the value of S? Can you get the value of S from this equation? I think we can get the value of S from this equation. So get the value of S is equals to 0.671. 0.671. Now let's talk about the second part. That for full saturation, that's 100% saturation. What is the extra water? What's the extra water content we have to add? What is the extra water content we have to add in the soil? So for degree of saturation equals to 1, I would say what is the for S is equals to 1, what is the water content we have to add? Let's say that this is water content 1. So I would say what is the water content 1? Is that E by G? Is that E by G assuming E remains assuming that E remains constant? E remains constant. That if I say that the value of W1 would be calculated from E by G, so your E is actually how much? So we need to calculate from the first equation, first statement. Once we got the value of S equals to 0.671, that we have that E SE equals to WG. From that we can get the value of E initially. That is actually WG by what you call as WG by 0.671. So W was there, 2.7 was there, and divided by value of S 0.671. So that value of E we can substitute here, and finally we can get the value of W1. So that's some value W1 equals to some value. Let's say that overall value is 0.2485. That's 25.85%. And initially we have how much water content was there? 15%. So we need to add the difference of the two. So additional water content we had to add. Additional water content is equals to 24.85% minus 15%. That is 9.85%. Let's take one more. Let's take one more. So we have to prepare a soil. We have to prepare a soil. So soil is prepared. Soil sample we can write. Soil sample is prepared by mixing dry soil. By mixing dry soil at water content, I would say by 10% of mass. So your water is that 10% of weight of solids. So we have to mix the dry soil such that weight of solids of the dry soil, weight of the solids is equals to 0.1 times weight of the water. So this is your actually water content is given that water content is given that water content is weight of solids, weight of water by weight of solids, that is 0.1. So at this ratio of solids and water, we have to mix the dry soil such that we can have the final soil sample. Okay. After that, find the mass of wet mixture. Find the mass of wet mixture. Mass of wet mixture. Okay. For how much volume? So we have to prepare one cylindrical sample. We have to prepare one cylindrical sample such that the diameter is 15 centimeter and the height is 12.5 centimeter. For preparation of this mold, for preparation of this much amount of volume, for preparation of volume of the mold, that means volume of the soil and the mold should be this much. So this much amount of for this much amount of volume of that particular soil mixture, we had to get the mass of that wet mixture. Wet mixture, mass of wet mixture. So that's actually mass of some soil plus mass of some water in that mixture. Okay. So it's also mentioned that the specifications for this mix is should be such that you're having 6% air content. So it should be at 6% air content. The mixture should be at 6% air content. Okay, 6% air content, and we need to calculate finally find the void ratio, gamma dry, also for the soil, if specific gravity for the solid is 2.68. So how many data we need to calculate for? We need to calculate for mass of the solids. I need to calculate for mass of the solids, mass of the water, such that I can get the mass of the mixture. Okay, and we need to calculate void ratio, gamma dry. So let's say that we have 6% air content. What that means? Well, that air content, that is volume of air by volume of voids. That is 0. That is 6%. 6% air content. So if I say that we have a general soil, if I have a general soil, we're having some air, we're having some water, we're having some solids, and I want air content should be 6%. That means volume of voids is let's say that this is total volume of voids, and this is let's say some value, and volume of air should be 6%, 0.06 of volume of voids. That means by the concept of degree of saturation, that should be 96%. Can we say that 94%? Degree of saturation would be 94%. That is volume of water by volume of voids. So volume of voids is actually volume of water is actually 0.94 times volume of voids. We can say that volume of water is actually 0.94 times volume of voids. Volume of water equals to 0.94 volume of voids. So this is your volume of water, 0.94 volume of voids. Okay. Now I would say, what is the total volume of the soil? Can you calculate what is the total volume of the soil required? So volume of the soil, that is volume of the soil. That's pi by 4, 15 square into 12.5 centimeter cube. So that volume of the soil is coming to be equals to 2208.9 milliliters or centimeter cube. This is also centimeter cube, we can write 2208.9 centimeter cube. And this is actually, this is because this volume is because of volume of solids and because of volume of voids. Volume of solids plus volume of voids. Can we say that? Now I need to solve for mass of solids and mass of the water. And there's an equation that's volume of solids and volume of voids. See, I have these two. I have the unknowns. I had to calculate for mass of the solids. That can be calculated from the volume of the solids. And I had the unknown of mass of water. That can be calculated from volume of the water. And volume of the water is related to that volume of the voids by this relation. Can we see that? So if I solve in that way, I would say that 2208.9 centimeter cube is actually equals to volume of solids is actually weight of solids by g of solids times gamma w plus volume of voids would be converted to that volume of water divided by 0.94. And volume of water can be converted to mass of water. We can write weight of water in terms of weight we are calculating. Then we can substitute the in terms of mass. Weight of water by rho, gamma of water, and that divided by 0.94 also. This factor of 0.94. Can we write that in this way? So we can see from this equation we would see only the unknown is there ws and ww. Ws is there and ww, so we can simplify it and substitute the value of gs 2.68. And this w here is in terms of mass, in terms of kg we can solve, because all of the data is in terms of those centimeters, kgs, etc. So we can solve that in that same way. So I would say that we are having some weight of solids divided by that 2.68 into 1 gram per cc plus volume of voids. We have converted that in terms of weight of water divided by 1 gram per cc into 0.94. So this is equals to 2208.9 centimeter cube. And in the denominator we are having that gram per cc. Let's say that we are having that gram per cc, 1 gram per cc. Now I would say that how can you convert that weight of water? So we have this equation, one equation, two unknowns. We have this one equation, two unknowns. So we should see whether we can replace this by some water content relation. So weight of the water is given, can be related to weight of solids by the water content relation. And that's mentioned that water content is 0.1. Water content is 0.1. So we can write that it's actually equals to, this part is actually equals to 0.1 times weight of solids. So finally you can solve for the weight of the solid is actually in terms of mass, that would be weight of the solid is equals to 4606.5 grams. So that's actually the weight of solids in terms of mass. And from that we can say weight of the water would be 460.65 grams. So I would say, what is the weight of the mixture? So weight of the mixture, wet mixture is equals to sum of the two, that is 5 times, that is 5067.19 grams. This is the weight of the mixture for that particular volume of 2208.9 centimeter cube. So we got one of the part here. Now we need to calculate gamma dry. Can you calculate gamma dry from gamma bulk? If I know that gamma bulk is gamma weight of the soil, weight of the soil mixture, wet mixture, weight of the wet mixture of the soil divided by volume of the soil and divided by 1 plus W. So we can get the value of gamma dry. Can we get? So weight of this we can finally solve for the gamma bulk actually. So gamma bulk is actually weight of the soil was 5.06719 kgs, 5.0619 kgs divided by volume of the soil was 220. How much was that? 2208.9, 2208.9 centimeter cube, and we have 10 to power minus 6 meter cube divided by per centimeter cube. And this is your gamma bulk, and we need to divide by 1 plus water content. and we have that 1 plus water content 0.1, so we can get the dry unit weight in terms of kgs per meter cube, in terms of kgs per meter cube. So gamma dry would be calculated equals to gamma dry equals to, in terms of, we are calculating in terms of what you call as density. So density that is 2.085 grams per cc, and let's say that this is also equals to g gamma w 1 plus e, and from that get the value of e. So that's actually the value of e is actually g gamma w divided by rho w, or rho dry minus 1. So get the value of e. Your e value is coming to be equals to 0.285. That was all about that problem. That was all about that particular problem. So we have two final problems. We have three final problems for your compaction.